Thanks. Many thanks for the invitation, Carlos. So it's also really a pleasure for me to be here. I'm really honored. Thanks for the invitation, by the way, and for all the arrangements. And yes, it's also a pleasure meeting again in a different context. I mean, from CTTC with you and your colleagues as well. So all this said, well, Carlos asked me to prepare a few slides before, say, the official presentation today about CTTC, who we are, what we do, just to have some background and be on the same page. And this is what the first presentation is about. So my name is Carlos Antón, as he said. CTTC is based in Barcelona, in Spain, actually not in Barcelona, but in Castelldefels, which is a town nearby, where, by the way, a number of football players from Barca live, by the way. I do not live there. Well, this is our building, and these are... Sorry? I thought it was... Okay, sorry about that. That is not this one. Share again. This one, screen number 2. Okay. Is it fine now? Now it's fine. So these are some pictures of our building and our facilities and labs. So we are in Barcelona. So if you ever say travel to Barcelona for some reason and you want to visit us, just drop me an email, and I will be happy to tour you around, of course. Now, it stopped working, or? I think you need also to connect on the previous one. Yeah, thanks. Good. So who we are? We are a non-profit research center. We opened doors in 2001. We say depend on the regional government of Catalonia, the Generalitat, who also pay for part of our running expenses, probably 40%, whereas the remaining 60% has to come from projects, national projects, European ones, projects with the industry that we have to obtain via fundraising. We carry out fundamental and applied research, both of them. Also, having a strong international collaboration network is important for us, with research centers all around the world. This is one of the reasons why I'm here today. And experimentation is important for us. This is where we have a number of labs and test beds, most of them based on own deployments that we use for our research activities. We produce some papers, journal and conference papers every year, and also we are supposed to contribute to R&D training for students, visitors, postdocs, and we've cost a number of them over the years, and also supervise master and undergraduate thesis projects. So this is to say everything in a few words. Technically, from a technical point of view, what is our know-how? These days, I mean, 6G is the topic for us. Been involved in a number of European projects on beyond 5G and 6G networks, dealing with different aspects, both terrestrial, wireless communications, and satellite communication, and the hybridization of both types of networks. This is high on our agenda. And the circle up there reads AI, ML, artificial intelligence, machine learning, which is my presentation today. So this is, say, also a vertebrating topic in our participation in 6G projects, also about edge and cloud computing, packet optical networks for the core networks of those, say, future communication systems, localization, be this through satellite communications, that is Galileo, GPS, etc., or via terrestrial networks. Sustainable networking, how to make sure that those wireless communications are, say, sustainable enough, low energy consumption, and things alike. And also one research unit working on services and security aspects. This is a very quick summary in just one slide of what we do. And in terms of headcount, we are 100-something people. It's a truly international research center with 24 nationalities as of today, with 80% of researchers, and the rest, it's direction and support, administrative support personnel that are part of CTTC. More than 50% hold a PhD degree, and the number of women both at the research team and in the management team is roughly 30%. This is CTTC numbers. Our yearly budget is roughly 8 million euro, and out of them, 4.8 in 2021 came from European, national, and projects with the industry. This is the external funding part, which comes from 40% roughly from public competitive, be them national or European, 17% from contracts with the industry, and 3% other funding like training activities. In terms of, say, business development, the growth rate in terms of, say, attracting funds over the last 6 years has substantially increased. Last year, we submitted more than 140 proposals with a success rate of roughly 71% in European programs, which is, say, quite good, and we are happy about that. This allows us to reach in the Horizon 2020 program, be the second largest R&D center in this 5GPP program, which dealt with 5G networks. And in ICT in general, we hold the 25th position in terms of funding, and also in terms of the number of projects that we participated, the numbers are quite similar in funding or in terms of project participation. This is, say, the public side of the funding. As for the private part, that is projects with the industry, this is the main services that we can provide for them, which includes R&D contracts, that is, say, direct contracts or subcontracts in publicly funded projects, license agreement, be them patents or software licenses, training, be it at CTTC or in company, also developing joint products in exchange for royalties. For instance, this is something that we've done a number of times, and also a variety of technical support and services like feasibility studies, consultancy services, the use of CTTC's lab infrastructure, or other due diligences prior to investment in startups, for instance. And also on-the-job training, be it through thesis supervision or exchanges of postdocs, for instance, also coming from the industry. Where our customers are? Well, some of them are in the US, Canada, many of them in Europe, as you can figure out, also in Spain, also in the Far East, like Japan or China. You can see our main customers are, say, equipment vendors like Cisco or InterDigital, Nokia, Huawei, also operators like KDDI, Telefonica is up there somewhere, and also a number of SMEs and startups. So most of them working either in the communications domain or in vertical sectors using mobile network communications. Also South Africa. So to sum up, what we do, advanced R&D activities, and also prototyping or product-oriented activities. We are doing both things at the same place. That is very helpful. We are quite active in Horizon Europe and 2020 projects, that is European projects. We try to provide end-to-end knowledge of communication networks. This encompassing multiple technologies, wireless, satellite, optical, as I said earlier, and multiple segments, access, aggregation, and core, and from the physical layer and up to the service level. Of course, with different degrees of, say, activity, because everything cannot cover in the same way. In addition to communication networks, also some skills on navigation and remote sensing. Most 50% of our staff members are PhD holders. We also try to have the best lab infrastructure we can get from projects and from industrial contracts to publish some papers and make close to product development. We cannot develop products because we are non-profit, but still, in a number of occasions, we almost designed the final modem, for instance, for power line communications, and the company just say, put the box on the wires. So we can get arbitrarily close to that. We are quite flexible in terms of contractual and IPR schemes and have hold a number of certifications and accreditations. So this is try to keep it short, like 10 minutes. I don't know if you have any particular question on this. And if not, I will switch to the second presentation. Is everything fine with the transmission? Should be? Share the screen. This is the slide. Can you see it now? Okay, so now the technical presentation, which is entitled Statistical Learning and Inference for Large Dimensional Communication System, which is kind of pompous title, I would say, but this is the title of the project that I'm presenting today, which is ARISTIDES. And the project, after all, it's... No, it is not. Okay. So this is the title, which is a bit pompous, as I said, but it's about AI ML, artificial intelligence machine learning, a model driven that is more traditional designs for beyond 5G and 6G radio networks, mostly for the physical and the link layers, that is the two lower layers of the OSI protocol stack. And this project is funded by the Spanish Ministry of Science and Innovation. So about this presentation today, I will briefly introduce the eSpeak information and signal processing for intelligent communications and the network and positioning research units of the CTTC, which are the two main research groups that take part in the ARISTIDES project. Then I will try and summarize what ARISTIDES is about, present some selected research results from papers that have been published in the context of this project, and also try and describe the testbed and experimental equipment, mostly the AI wireless lab, which is the one mainly involved in this project. Then I'll try to briefly describe one demo on AI that we ran at the European Communications and Networking Conference back in June this year in Grenoble, in France. List some publications, and well, this project is ending in 5 days, 31st of August. So then I will try and describe what comes next, which is the follow-up project to ARISTIDES, which is called 6G INA, as what we'll explain later on. So the two research units in a nutshell. First one is eSpeak, which is, to make it short, it's signal processing and machine learning for the physical layer, for communication and mostly the physical layer. We are 9 researchers in total. 5 of them are permanent. The head is Jesus Gomez Vilar de Bo. We have 4 non-permanent researchers, and the focus, as you can see there, is signal processing, machine learning, and information theory for communications, notably the physical layer and the link layer. This is the focus, but I will describe this in the next slide, so I'll skip it for now. And our focus is quite theoretical, I would say, but we are also, running a number of experimental activities and doing some experimental work more recently. About the main research areas of our research unit, first of all, it's say physical layer functions like coding, equalization, modulation, demodulation, and how they can be successfully implemented via AI and ML schemes. This is the first area. For instance, you can use the autoencoder to model the transmitter and the receiver as deep neural networks, and training in order to reach some performance factor, which could be sample rate or any other related measure. Not only, learning those physical layer functions separately, but also jointly learning more of those functions simultaneously in order to make sure that the resulting system can readily reconfigure and adapt to a number of channels. Some of them are intractable, with models, and then this is where data-driven approaches turn out to be very helpful. This is the first area for the physical layer. Now, for the link layer, also doing some work on MAC protocol learning. This is one of the projects that we are running with Nokia Bell Labs in France, and it's about learning MAC protocols via deep learning tools and deep reinforcement learning tools, multi-agent deep reinforcement learning, for instance, like you can see the schemes there, and it has also to do with semantic communication. So how can we successfully use data-driven schemes in order to learn MAC protocols, which are not meant to transmit general information that is bits, but bits for a specific task. So it's not that important, the bits, but what those bits mean. What is the meaning? What is the semantics of those bits? And with this, you can further optimize the performance of those MAC protocols. And we plan to design novel ones. What else? On the more classical side, if you want, on the signal processing side, Topics which are important for us is extremely large antenna arrays, with antenna arrays which are made of a very high number of antennas operating at very high frequencies like terahertz and above. This means that we cannot assume that we are operating in the far field regime with planar waves, but we are in the near field regime. With spherical waves, the concept of beams is not there anymore, but we can place information, say, in specific points of the space, which can help when it comes to blocking, for instance. It's very important to understand the wireless medium because we are operating in frequencies which are not, say, the ones we are more familiar with, how to successfully design the transceivers, how to design communication protocols, and learn how those systems with a very large number of antennas behave asymptotically when the number of antennas in 1 or 2 dimensions grows large. Another important area for us is cell-free MIMO systems, in which users are not associated to only one base station, but served by a number of neighboring base stations, which allows to have a more uniform coverage, as you know very well. So this is also a very important area for us. This area, important aspects here are synchronization, radio resource management, how to design the pilot assignment techniques, or how the fact that the front haul has a limited capacity, how this can impact when it comes to designing those cell-free MIMO systems. And finally, again, from a, would say, more classical perspective, signal processing perspective, well, how to design new waveforms, new modulation schemes, or coding algorithms, mostly for spectrum coexistent tasks, for cognitive radios. For the waveform design, we are working quite extensively on the filter bank-based multi-carrier modulations, on how to make those receivers robust to Doppler, which is, for instance, what you can find in deep space communications, because the satellites or the probes are moving at a very high speed. So we have to make it robust to high Doppler or to frequency selectivity. Also, the design of short block length codes. This is something we did for Huawei in the past for ultra reliable low latency communications, how to design, for instance, LDPC codes which are suitable for systems with very low latency, and also to the implementation of LDPC or polar software decoders, which are the ones used in 5G for real-time performance. I mean, this for 5G protocol stack of 5G network, this is something that we did with a local company called Software Radio System. So the emphasis there was on implementation aspects, not only on the design of those schemes that actually were already given for us, but more on the implementation aspects. And this is the other area that participates in ARISTIDES, the navigation and positioning area. 10 researchers, 6 and 3, so 9 researchers in total. And here the emphasis in signal processing for navigation, not for communications, but for navigation. Good. Now, as for ARISTIDES, what is the project about? Well, this has a number of objectives. First of all, it's about developing AI/ML algorithms and using tools from signal processing to aid those AI/ML schemes. So this is about algorithmic development and tool development, and then it's their application to the design of beyond 5G and 6G network, which is our main application area. Also, we plan and we indeed implemented some of those AI/ML approaches, implemented them in proof of concept demonstrators, as I will discuss in the final part of my presentation. These are the objectives of the project: algorithmic design, application to wireless networks, and implementation of selected concepts. I am the co-IP for this project. This is the total budget, and as I said, it's ending by the end of August, and it's funded by the Spanish Ministry of Science and Innovation. So on the algorithmic design and tool development, these are the main areas. I will describe some of them later on, which is bivariate polynomial coding. I will explain those concepts, kernel matrices, encoded caching systems. And then when it comes to applying those schemes to wireless networks, these are the main areas for clustering schemes in MIMO-NOMA, multiple input, multiple output, non-orthogonal multiple access schemes. This is for clustering approaches, how to effectively place UAVs in a 3D setting in order to provide communication network while sharing the spectrum. Also, beam selection in millimeter wide bands, hierarchical beamforming for random access channel, how to when in machine type communications there are collisions of the packets sent for random access channel, how to effectively resolve them. And also one more on clustering for hierarchical channel clustering, again for MIMO aspects. These are the main research areas of the project. This is the experimental equipment that we've been using in the project. Some of this equipment has been, like this multi-user MIMO testbed, has been developed during the project and for the project. It has a number of MIMO arrays. This 4x4 is for the base station, but plus there are 3 UEs with smaller planar arrays that we are using as well. This was developed during the project and used in the project, but it's not the only experimental infrastructure that we are using. For localization aspects, we have 2 types of infrastructure. First, ultra wideband testbed, which is used in our navigation and positioning lab, which is meant to implement algorithms on factor graphs and Bayesian inference for indoor localization. This is what this second group of lab infrastructures is meant for. And also for outdoor communication, that is via Galileo and GPS, we are using our GNSS software-defined radio receiver. This is a picture. This is the rack for the Galileo software-defined radio receiver, and these are the antennas which are placed in the rooftop of CTTC. Now, what are the main outcomes of the project? So a number of articles and conference papers. Of course, this is taken for granted when you set up a project like this one. Also some open source code publications, mostly for the navigation and positioning part, because they are using this software-defined radio receiver. 3 data sets have been published, 2 on wireless communications, 1 on localization aspects, and have been uploaded to Zenodo. There's one PhD thesis that is ongoing and that is being supervised. And we have managed to get involved in a number of European projects, also projects funded by the European Space Agency and national programs, which are related to the topics of the ARISTIDES project. So in terms of dissemination, we ran a couple of demos. One of them was back in February at the Mobile World Congress in Barcelona, which was very well attended. Even the president of Catalonia attended our booth. I was explaining him what the demo was about. I don't know if he understood much, but he looked interested, which is what he's supposed to do, I would say. And also at this UCNC summit in Grenoble back in July, where, by the way, I mean, TII booth and our booth were sitting one in front of the other, by the way. So we were neighbors at the exhibit. So very good neighbors, by the way. Also, some technology transfer project and dissemination activities with the industry, with Huawei on the design of short-length block codes. NVIDIA, we had a visitor from NVIDIA in Germany, working with, I'm sorry, I forgot the name. So they were visiting us back in July, and we have produced a Python notebook that will be uploaded to their website and to ours on MIMO based on their Shona library. Some of you might know it. So this is some dissemination activities that we've done doing jointly with NVIDIA, a course for Airbus on AI/ML for cognitive radio networks, and some European projects that we are doing with World Sensing, which is a Catalan company. And this is for training students in the AI/ML area. This is what we're doing. Now, as for the data sets I was mentioning a few minutes ago, these are the ones that we managed to produce in ARISTIDES. One for indoor wireless channel measurement, which is for a point-to-point channel. And this is meant to be used by researchers willing to do some experimental work, but not having, say, the equipment, the USRPs, for instance, to generate real data. So you can use this data, run your algorithm in it, and that's it. So this is why we uploaded it to Zenodo, this public repository. It's available there. You have the link. In case you're interested, you can download it. And the other data set was for indoor ultra-wideband measurement. There was a number of anchors deployed in the walls of our navigation and positioning lab, which is this one here. They were transmitting the signals, those anchors, to a node which was placed in the middle of the lab. And the signals that were transmitted and all the protocols were recorded and put together as a data set. And this is, again, was uploaded to Zenodo and can be used for research on AI/ML for navigation and position. Now, As for another priority of the project was to carry out very active collaboration with institutions worldwide. And well, for some reason, the map is not there. So you can see it. Okay, so it's about the projector then. So there is a world map here, and you can see the teams and the universities with which we have collaborated in the US, in Canada, in several places in Europe, like EPFL, in Switzerland, Leuven in Belgium, Imperial College in London. In the Middle East, we collaborated with King Abdullah University of Science and Technology, with Professor Alouini, some of you might know him. And also with some institutions in the Far East, like the Halim University in Japan or the Shintal University in China. So, and we are open to additional scientific collaboration with other groups all over the world. So if there is some mutual interest, some topics that we want to collaborate, for instance, with you, we are very open to that. Just drop me an email and we will be happy to discuss. Of course, there is no project that can avoid having a project website. Ours is not, say, particularly fancy, I would say, but all the information is there. Here's the URL, and we have all the papers there, videos, demos, etc. Everything is uploaded there. So if you are interested, just have a look at it. Also prepare a promotional video for the general audience, which was kind of a challenge, I have to say, starting with the language, which is not the one we are used to in our daily work. So it was about explaining to the general audience what 6G is about, what are the various applications, extended reality, virtual reality, low latency communications, what is the role that AI can play in the design of 6G systems. Also, a challenge was to explain what the physical layer of a communication system is for the general audience. But I mean, with the people from this company that produced the video, well, that was very, say, easy to do that. I mean, with a number of diagrams and blocks. We also explain our experimental activities in wireless communications and also in localization, indoor localization and outdoor communication with terrestrial and with satellite signals, GPS. And this is my co-IP, Adrian, and myself trying to explain also what were the main achievements of the project. So there is the URL there. If you want, you can have a look at it. As for projects which were a spin-off of the project, there's this European one, which is Interact, which is a network of researchers working, all of them, on AI/ML for communications that will run until October 2025. This is a cost action, mostly for networking activities. National project working on beyond 5G and 6G communications based in 3D networks, that is terrestrial, flying platforms like UAVs, and also satellite-based communications, trying to put the three together, also with a strong AI/ML component in doing this. Windmill, which is a European project for training researchers, mostly PhD in AI/ML, and this project on with the European Space Agency, what was about designing modems based on, say, frequency shift keying, which sounds like rather old stuff, but it can be very useful and very low energy consumption when the data rates to be transmitted are low. And also 5G Lab, which pays for part of our infrastructure. The project with Nokia Bell Labs, we was on the design of MAC protocols and semantic communications, the course for Airbus, the project with Huawei on short-leg cloth codes, and the project with SRS about LDPC and polar codes for 5G new radio, implementation of those codes. This is the main projects related with the contents of the ARISTIDES project that stem from it. Now, going to the technical stuff. What are the main areas? For the first, say, work package, which is about algorithmic development and preparation of development of tools for AI/ML schemes, we have this first one. I don't know if it is, because all the titles are, it's difficult to read. You can see it online. Okay, no problem. So this one is about bivariate polynomial coding for efficient distributed multiplication, matrix multiplication, which sounds like a bit of a strange, but let me tell you in a few words what it is about. The project is that, well, performing matrix to matrix multiplication is a time-consuming task, but still is very useful for many machine learning algorithms, for instance, for the computation of the gradients in deep neural networks or for logistic regression. So this is an important problem for ML algorithms, and this is why we have to design this matrix to matrix multiplication in an efficient manner and fast. And one way of making it faster is by using distributed computation, which means that rather than doing it in a master device, which is centralized, we split those computations into a number of computing devices. So these computations are, say, some of these are matrix to matrix multiplication. So you send some rows and some columns from the first column, from the first matrix and the second matrix to each of those workers, and they do the computations and send back the result to the master. The problem is that some of them might be too slow, and you cannot finalize the computation until all those local or sub computations are achieved and sent back to the master. So it might take too long, and we have to wait for the slowest one. But one thing of avoiding that is by introducing some, say, channel coding in this original matrix. So there is some redundancy. So you don't send the matrix themselves, but the matrix with some redundancy. This means that even if some of the computations, the sub-computations are not received back in the master, you can reconstruct them from the other computations. So we have four workers and only 3 of them send back their computations. You can reconstruct the other computation for the 4th one with the 3 ones that have been received. You do that with some coding. The previous work was using univariate polynomial coding, but this is not very efficient, in particular, when you want to take into account that some of those workers have more computational capabilities than others. So you could send 2 sub-blocks to this one because it's a faster CPU and only 1 block to this one. And if you want to do that, univariate polynomial coding is not very efficient. We have to use bivariate polynomial coding, which allows to reconstruct also the original matrix, which is spread in a number of sub-matrices, not with absolute certainty, but with some high probability. So this is the fact that this is the price that you have to pay, that it's not reconstructed for sure, but with a very high probability. This is the price that you have to pay for speeding up this computation, because you are assigning some more work to some workers than others. And these are some representative plots. Now, more on the application of machine learning and AI techniques to specific communication problems. First one is hybrid beamforming. This means that you have a base station equipped with multiple antennas and a number of single antenna terminals. And it's called hybrid because there is a digital part, baseband part, and the analog beamforming part. So analog beamformers and baseband beamformers. So what we want to design is the analog part of this beamformer network, and we have a number of beamformers to choose from. These are beamformer 0, beamformer 1, and beamformer 2, and we need to decide which is the best one to use according to the location of those terminals that are spread all over the cell. So what is the best beamformer to use? This is about beam selection in a hybrid networking context. And to do that, we will be using direction of arrival information. So we know what is the direction of arrival of those signals and what is the power received from each of those users. And with this information and an MLDL approach, which is a deep neural network, a multi-layer perceptron, we decide what is the best analog beamformer that we will be using in this analog beamforming block. We compare the performance of this DNN-based scheme with more, say, simpler schemes like K-neural networks or support vector classifiers. We compare the performance, and we find out that in terms of sum rate, this is actually the percentage of the optimal sum rate that you can get with the optimal approach, which means just trying all the beamformers and finding out what is the best one, which is the best thing you can do, but it's, say, computationally intensive. So this is the red curve. So in this case, the percentage of the optimal sum rate is 100%. If you say pick one of the beamformers at random, this is what you get with the black curve. So this is randomly selection of beamformers. And what you can get with a DNN-based scheme for beam selection is the green curve, which is very close to the performance achievable with the optimal exhaustive search beam selection method. So this is the good news. And with the classical ML approaches, well, there is some penalty that you have to pay. But with DNN, that is deep neural networks and the multi-layer perceptron in particular, you get a performance which is very close to that of the optimal scheme. Now, a different problem here is about the user clustering for MIMO-NOMA networks. What is the problem here? We have a base station with multiple antennas. We have a number of users spread in a cell, and we have more users than the number of antennas in the base station. So that means that we have an overloaded system. This is a non-orthogonal multiple access scheme because we have more than one user using the same resources in the time of frequency domain. And since we have a number of antennas at the base station, we will generate two groups. So a subset of the users will be detected first with a linear receiver, like a linear minimum square error receiver. So we have the first group, they are detected, detected the signal, subtracted the interference, and then we detect the second block. So it's about deciding whether the users in the cell should be detected in the first place or in the second place. So we have a number of users, and the answer is group 0 or group 1. So this is a classification problem, a multiple classification problem with two groups. And we are using some random matrix theory because we are using a multi-layer perceptron to do the task. And we need to train this multi-layer perceptron and tell the multi-layer perceptron for a number of examples. I mean, what is the cluster that each user belongs to, either the first one or the second one, in such a way that you maximize the sum rate at the output of the receiver in the base station. So you have to generate a number of examples, and you have to compute the sum rate. And this is like a cumbersome problem. In order to speed this up, the calculation, we use the random matrix theory, which means that we have a closed form expression of the sum rate when the number of antennas in the base station and the number of users in the cell grows to infinity. And this allows for a faster training of the multi-layer perceptron running in the base station. So in terms of performance, what do we have? So we have the sum rate at the output of the receiver in the base station as a function of the signal to noise ratio. So this is the optimal sum rate that you can get when you simply try all the possible combinations of users being allocated in the first cluster or in the second cluster. So this is, again, an exhaustive search, which is something that we definitely have to avoid. But this is what we can get in terms of sum rate. The red curve is the proposed scheme. We are using a feed-forward neural network there, so we can get arbitrarily close to the optimal performance. And if we use a suboptimal approach, this is called power-based hierarchical clustering, which is, say, a simplified version with very low complexity. You have a price to pay, I mean, for going for simpler approaches. And if you simply assign users at random, the sum rate that you get is the one shown by the black curve. So again, we have a lot to gain from using deep neural networks for clustering users in MIMO-NOMA scheme. That is the idea. A different yet related problem is deep learning-based channel estimation and data detection for MIMO systems. So we don't have a multi-user MIMO system, but a point-to-point MIMO system, one transmitter, one receiver here. And we are interested in designing the symbol detection and the channel estimation blocks. So, for the channel estimation part, we are using a neural network, again, a multi-layer perceptron, and we compute here the estimation error of the channel impulse response, the mean square error in the channel estimation process as a function of the signal to noise ratio for two schemes, a linear least squares, which is kind of very, say, well-known approach, and a neural network-based one, based on the multi-layer perceptron. You can see that the error is substantially lower for the neural network-based scheme, basically because it can be, say, regarded as a Bayesian-like approach. We have like knowledge on the statistics of the channel by using multiple examples, whereas the linear least square scheme is a classical one, which is one shot and does not use the statistics of the channel itself. This is a regression problem because we have as input, we have the received signal, and the output is the estimate of the channel response. So this is a multi-output regression problem, multi-output because this is a matrix that we are estimating here, the channel matrix. For the second part, the symbol detection part, so it's about getting the received signal, the channel estimate that we obtain with the channel estimation process, which is also based on neural networks, and it's about deciding if it is a 0 or 1, what was transmitted. So this is a multi-label classification problem. Again, we are using DNN schemes, deep neural networks. And what we can see here in this curve is that we are getting a performance which is very close to that of the maximum likelihood detector. Let me show you what you have here. So this is the symbol error rate as a function of the signal to noise ratio. So the best thing you can get, it's the black curve. So this is the lowest symbol error rate as a function of the signal to noise ratio. The blue one is what you can get with a zero forcing receiver, which is linear and suboptimal, the blue one. And the performance that you obtain with deep neural networks are the red and the magenta curves that are down there, which are substantially closer to the performance of the maximum likelihood or optimal detector than to the zero forcing detector, which lies above, clearly above. So we have a lot to gain from using neural networks for symbol detection tasks in this point-to-point MIMO setting. Different problems. This is about collision resolution in random access. So we have slotted aloha random access scheme. We have two users in particular, and they are transmitting symbols. They are transmitting symbols with orthogonal modulations, like the ones used in LoRa. Some of you might be aware of this. This means that the waveforms are orthogonal to each other. So as long as they transmit different symbols, there will be no interference between them. And there is no need to send pilot symbols to estimate the channel. This is why it's orthogonal modulation scheme. So what is the problem? Crosses is user 1, source A. Circles is the second user, source B. So these are the possible symbols to be transmitted. So as long as the users transmit different symbols, which means different rows, there is no interference, no interference, no interference. The signal can be retrieved for both users. But in this point, they are transmitting exactly the same symbol. So here there is a collision, a symbol collision that we have to, say, fix somehow. And this is what we are doing with a number of tools from signal processing and machine learning to resolve those collisions. So the system is confronted with two problems. First of all is to decide what symbols were transmitted by user 1 and which symbols were transmitted by user 2, because in those systems with orthogonal modulations, you don't have a sequence that identifies the two users, but you simply get two symbols and you need to decide whether symbol 1 belongs to user 1 and symbol 2 to user 2 or all the way around. So we have to map symbols to users. This is the first task. And the second task is to resolve those collisions. And this can be done by using a combination of machine learning tools, in essence, what is called hierarchical clustering methods, and a number of optimization tools like ADMM or transportation theory, which is the Hungarian method. So I will not go into the details, which is a bit involved, but by using a combination of machine learning techniques and classical optimization techniques, it is possible first to decide to retrieve the two users separately and to resolve the collisions. This is what the project is about. Here we have the performance in terms of word error rate, in terms of successfully transmitted symbols, again, as a function of the signal to noise ratio. The dashed line, it's, well, in the case that those symbols, all of them belong to the same transmit user. So you don't need to decide the user that they belong to. In this case, this is the lowest word error rate. Whereas for the proposed scheme, that is the combination of machine learning, optimization, and transportation theory, the word error rate is slightly higher, but notably much lower than you can get with other benchmark algorithms, which is the Hotan scheme or other non-coherent modulation scheme. So again, we are getting a performance which is quite close, in particular for low signal to noise ratio, to the optimal performance that you can get when there is no interference between those two users. one more scheme, and I will go directly to the demos for the benefit of time. It's about using hierarchical beamforming in random access channels. So what does it mean? We have a base station which is equipped with multiple antennas and a number of users spread all over the cell, and they are trying to get access to the system, the initial random access of the system, which is well, in LTE and also in 5G new radio, it's quite inefficient due to the collision of the preambles. If two users pick the same preamble to get access to the system, there is a collision and none of them gets access to the system. So what is done in, say, classical 5G or 4G systems is, well, telling some of the users, please wait. If there are many users attempting to get the channel resources simultaneously, you tell some of them to wait for some time, which is what is called access class barring, which is fine, but of course introduces some additional delay. And this is what we attempt to avoid by exploiting the spatial dimension. With this meaning that since the base station has multiple antennas, as long as there are many users attempting to get access to the system, we will be using different beams in such a way that more than one simultaneous access is allowed to the base station. In this way, we can reduce the access delay in comparison with the single antenna system. But of course, we need to decide when we need multiple beams and when we can manage with one single beam. The reason why we try to avoid using multiple beams all the time, which would be the obvious solution, is that when you have multiple beams at the base station, you have to use more hardware, the energy consumption is higher, and you need to allocate some extra computational resource. Otherwise, I mean, using always all the beams would be fine, but this is something that we want to avoid to keep the energy consumption low at the base station. So again, the question is, can we exploit the spatial domain, say the fact that we have multiple beams, to reduce the delay in the random access to the system? And definitely we can do that. We are using two reinforcement learning schemes to that aim. Specifically, you have two reinforcement learning agents. The first agent decides on the access class barring factor. That is, I mean, to what percentage of the users you will be telling, please wait and transmit later. So if it is 10% of the users, 50%, or 90% of the users that need to wait for some time. This is the access class barring factor. And the other agent decides on how many beamformers we should use at the base station. If it is one beamformer, two beamformers, or 10 beamformers. The more traffic, the more beamformers we will need at the base station. So at each period, this is DQN because you are using deep Q networks. The first one is DQN ACB, the one that decides on the access class barring factor, and the second agent, the second deep Q network, which is called DQN frame, decides on how many beams to use at each frame. So in the first frame, we only are using one beamformer, whereas in the second time frame, we are using 3 beamformers, 1, 2, 3, and for each of those frames, we have a different access class barring factor. Here we are allowing fewer users to transmit. Here we are allowing more users to transmit over those 3 beams in particular. Again, what we are showing here is, well, the blue line is the number of active terminals. So here we have fewer. When we have fewer terminals, we are just using, in this particular case, 2 beams. But here we have more terminals trying to get access to the system, and we are using 4, 5, and 7 beams in parallel, pointing at different areas in the cell. Now, when the traffic decreases, we are using only 1 beam, so it's omnidirectional, and so on and so forth. And those deep Q networks, what they do is they are tuning adaptively the parameters, how many beams we should be using, what are the access class barring factors, and the information that it is used to decide on this is the number of collisions detected, essentially. And by this, we can select if the beams have to be narrower or have to be broader and have one or multiple ones. What do you gain from this? Here is the, cumulative density function of the delay for a system which uses no deep reinforcement blocks. We always let all the users to transmit, and we are using all the beams simultaneously. Is it good in terms of delay? Well, it is. The results are given by this black curve. So, well, it's definitely better than using only the the access class varying factor, which is the red curve. You gain something from this at the expense of having extra energy consumption at the base station. But if, in particular, you use two DRLs, two deep reinforcement learning, two deep Q networks, adjusting the access class varying factor and also the number of beams, well, which is the green curves, this helps further. I mean, the delay is lower, in particular for terminals with low priority. Whereas for high priority, the gain is not that much. It's comparable to what you get when you only use access class varying. But still, for some scenarios, it pays off having multiple beams and changing the number of beams and the access class varying factor on the fly in order to give access to more terminals to the system. I will skip those two other examples for the benefit of time, and I will go directly to having a quick look at the experimental equipment, our AI multi-user MIMO testbed, which was shown earlier. So this is the base station. There are 3 user equipments there. The third one, you cannot see it, but it is there, with a number of arrays with 16 antennas for the base station and 4 antennas for the user equipment. So this is what we use for our experimental work. And each of those 3 user equipments is equipped with a number of USRPs plus a number of GPUs to run the machine learning algorithms, which are provided by NVIDIA. Also some workstations for the simulation, the planar arrays that I already talked about. So what are we doing with this equipment? So for instance, we prepared a demo for UCNC 2022, as I said earlier, on AI-assisted non-orthogonal maximum multiple access schemes for the uplink. So what is all this about? Well, it's a system with 2 users, 2 user equipments, user equipment 1 and user equipment 2, which are trying to gain access to a base station, transmit data to a base station, which will be here. What will we do in the classical setup? So we have a number of bits, data source 1 and data source 2, and we, for instance, we can use a QPSK modulation, which means that we are mapping those bits into a number of symbols in the I and Q components. So you get one of those regular grid patterns that are the constellations, which are the symbols to be transmitted. Then you send them to the OFDM modulator and to the RF chain for transmission. You do the same thing, and each user has to transmit at a different power level, because on the basis of those different power levels, you can multiplex multiple users on the same resource, because this is a NOMA scheme. At the base station, we decode the signal, we demodulate the OFDM signal again, and then we use successive interference cancellation for the decoding, which means we detect one of the 2 users first, and then subtract the interference and detect the second one. This is a toy example, but this is something that we are running in a demo, so it cannot be that complicated. And then we detect the symbols transmitted by user 1, compute the block error rate for user 2, and compute the block error rate. So this is the traditional scheme. And the successive interference cancellation leverages on power difference. That is, it detects the stronger user first, because the signal to noise ratio is higher, and then the weaker user in the second place after the first user has been detected. So this is what you do for the classical system. But what can we do better by using neural networks? Yes, we can do better by designing more sophisticated constellation. We are not, say, aiming for a regular pattern like UPSK, but going for something more imaginative. How can we do that? We are replacing, as you can see, the QPSK mapping block from bits to symbols by an AI mapper, and also the successive interference cancellation receiver by an AI-assisted SIG decoder. What is the tool that we are using? We're using an autoencoder, which is a well-known, say, tool for in deep neural networks, and the encoding part is used for the transmitter, for the for both user 1 and user 2, and the decoding part is used for the signal interference cancellation block at the base station. What do you gain from this? You gain the following, that as you can see here, this is the constellation that is being generated. So it's not the classical, say, QPSK constellation, but a more sophisticated one with, as you can see, and blue color is user 1, red color is user 2. So this is not, say, a regular constellation pattern, but something more sophisticated, where symbols of each user are placed in different subspaces in such a way that when they will be detected at the base station, it will be easier for it to retrieve those symbols. So this is what we gain from using neural networks, getting constellation designs which are better for detection at the base station, which is also using a neural network for that task. So this is the setup that we use. We are using two USRPs. One of those USRPs is playing the role of the base station. It can work with QPSK modulation or with this autoencoder, which we refer to as AI assisted. There is over-the-air transmission, so the symbols were effectively being transmitted over the air. And then we had two user equipments, user equipment 1 and user equipment 2, which transmit the symbols to the base station. Here we show the constellations being designed. This is for the QPSK scheme. You can see the regular pattern that you know very well. And the constellations that are designed by AI have absolutely nothing to do with the ones designed by a QPSK, but they exploit more efficiently the channel and allow to get a lower symbol error rate, as we will see in a minute. Because we are detecting the block error rate in real time at the receiver. So this is the real-time plot. This is for user 1 and user 2. For user 1, the blue curve is the block error rate that you get with QPSK modulation, and red one is the block error rate that you get with AI. As you can see, it's lower for AI, which is good sign. And same thing goes for the second user. Yellow is QPSK, green is AI. So again, the block error rate is also lower when you use AI-based modulation schemes. If you average over time, this is what you get for user 1 and for user 2. For user 1, the blue curve is with AI, and red curve is with QPSK. So again, there is a gain from using AI modulation schemes for both user 2 and user 1, and the gain is roughly 2.5 to 3 dB gain with respect to using QPSK, which is quite substantial, I would say. And that's it. This is a number of publications. You can find them in the slides that I guess you will circulate later on. So I will generate the PDF. So if you are interested in some of them, you can download it from the project website. Journal articles, conference papers, you can see all of them there. And we are coming to an end. Coming up next, the project ends in August this year, but we submitted a follow-up proposal to the Ministry of Science and Innovation, which is called 6G AINA, which is on the design of artificial intelligence native 6GA interfaces, which matches very well the topics that were addressed in the previous project, ARISTIDES. So it's a follow-up project. And these are the keywords that we use for this new project, which is already approved for funding and that we will start on September the 1st, which is excellent news. For once in our life, there is no gap in between the two projects. We'll be using multi-agent deep reinforcement learning techniques, also for communications and also for positioning, distributed computation schemes for the edge, rate splitting multiple access, MIMO as we used in the past. Well, you can see the keywords there, extremely large antenna arrays, which is also very high in the agenda for our research unit, and also implementing some of those algorithms in proof of concept demonstrations in our experimental platforms. So the show goes on. We'll be working in those topics. So if you are interested in some of them and you can see some collaborations, we will be glad to discuss them and collaborate with you. This concludes my talk, and thank you very much for your attention. You can have a couple of questions.
question. Yes, you saw many MLIs were many specific cases, right? For example, in the demo, you saw CTTC method. I wonder if it's
You mean this one, the demo?
for example, you saw CTTC method. I wonder if you play with people that you can train a foundation model that for small configurations that you can apply to, for example, for 16-con, DCSA, or different scenarios, and say maybe also for Mac that you can use for grant tree, you can apply to grant-based or different of these configuration without retraining the model or with a small configuration.
Okay, so if I understood correctly, your question is, we are, say, running this demo for one modulation scheme, which is QPSK. What happens if we use different modulation schemes? Is this the question?
Yeah, like a model is trained for QPSK, for example, like you say you have data trained for QPSK. So maybe you train a large model for different scenarios, and maybe you have a small configuration, you can use it for different scenarios.
You could use higher order modulation and make the spectral efficiency higher. This is something you can definitely do. Well, the good thing about using AI, and this is something that we realized working with NVIDIA in July, is that, well, for a given, say, this is a multiple access channel, you need to decide what is the modulation scheme to be used at the transmitter. And you have to make sure that the modulation scheme used is below the channel capacity, because otherwise transmission is not possible. So either for, say, traditional schemes, you need to decide on this, what is the optimal modulation scheme to be used that takes as closer as possible to the Shannon capacity limit. But if instead you use AI-based schemes, this modulation, these constellations that sorry. So these constellations that the system, say, automatically designs are already optimal in terms of sum rate. So this is done, say, automatically. This is the best thing you, I mean, if trained properly, this constellation schemes gives you the highest sum rate capacity for the setup. So you simply forget about that. You don't have to pick the modulation scheme, but AI/ML does that for you, which can be very helpful. I mean, it does not have to be the optimal, but this is something that, say, can be done automatically. So you are relieved from that task. And this is something that the autoencoder does for you. So that's the interesting point. One more advantage of using AI/ML. And the reason why we learned that is because, I mean, we tried to go from QPSK to a higher modulation scheme, which then we realized it was beyond the Shannon's capacity limit. So it stopped working. It will be optimized for higher modulation scheme, or you have to retrain in a high modulation scheme scenario. Sorry, I'm not sure if I got your point. And if you go for high modulation scheme, do you have to retrain your model, or you have small configuration, or that you can also, the result is also optimized for higher modulation. But the system is not being trained for QPSK modulation schemes. We are designing new modulation schemes. We are designing new constellations, to be exact. So this constellation is the output of your training. So it's not, I mean, the QPSK is just the benchmark. So we are not using QPSK in combination with AI, but doing something different with AI. That's the thing. What is the size of the constellation? So the second question is? The geometry is, yes, it's different, as you can see. I mean, it's like for the third user. Yeah. We did not try, to be frank with you. So if we have 3 users, I mean, it will be a constellation in such a way that it attempts to orthogonal users as much as possible. It depends on the propagation conditions in the complex plane. Well, actually, it's 3 dimensions. Which is I, Q, and the eye for the next symbol. So this is why it's depicted in this 3D setting.
Because this may have the normal. It's one of the questions that I have. If you add this, how you get the overlapping of the users? Maybe you can increase it to be properly kind of.
By properly designing the constellations. That's the idea.
Because when you say the clustering and so on, I was wondering how many users do you cluster and how many you can overlap? Because this is one of the limitations of the normal.
Exactly.
Go far away than 5, 4, maybe maximum. And if the channel is more complex, then okay, it's another story.
Which is exactly what you get here. I don't know if you can read. I mean, in the classical conventional QPSK, we have like the two modulations superimposed. So it's QPSK and a smaller QPSK floating around. This is what you get. And this is what the receiver has to deal with. But it's everything is in a two-dimensional plane. Here, instead, we have 3 dimensions, which makes things easier.
This looks like spherical modulation with an angular inclination.
Mm-hmm.
Maybe test it with photographs to the phase noise.
Well, it makes sense to me, what you said. I mean, it's potentially, yes, more robust to phase noise. I agree. This is something that we did not try. I mean, we're trying just to do something, keep it simple for the demo. But I agree with you that because of the shape, I mean, could be more robust to phase noise. I mean, to rotations.
One question? Yeah. I have one comment about the user version. The consolidation is considered very speaking.
Sorry, say it again about?
The user version, there the consolidation could be using with speaking because it seems to be more robust, especially if you are dealing with interface information and it's considered useful antennas.
Exactly. This is what we're doing right now. I mean, going from NOMA to rate splitting multiple access and trying to say cluster users, not for NOMA, but for rate splitting multiple access, which is say, NOMA is known to be non-optimal for when using with multiple antennas. So MIMO NOMA, I mean, there are some gains that do not add together, but they do if you use rate splitting. And this is exactly what we are trying to do now.
Antenna and interface CSI rate splitting in MIMO NOMA doesn't work that.
Yes, fully agree. These were our first attempt, and then we are going. RS rate splitting multiple access was one of the keywords listed for the follow-up project, and this is the reason why.
But it's not going to make a user person for there is no need. You can handle the users and with a single layer of
Yes, we have started with a single layer rate splitting multiple access to start with, and this is something that, well, the paper is in production right now, to be exact. So this is something that we are planning to publish very soon. Yeah, starting with one layer.
MIMO with the channel train observe the networks, estimation and so on.
This one, you mean?
Yes. So this works when you are stuck.
Mm-hmm.
When you try and move a little bit, because we tested the 2 models. One it was for the vehicle to vehicle, okay? That is, we have to increase the mobility, and we tried also to compensate the effects of non-linearity of the receiver. So the problem is that when you start,
If it changes, then what?
no, the problem is that you need always something deterministic, even with 2 pilots, it's not really true, and then you train. If you train first and you do estimation, you are completely out because the propagation of the errors that the CNN or DNN is doing will go through all the system. That's why you have to start with something deterministic, even not complete, and then you do the training. So the current definitions of the FX training, deterministic, semi-deterministic training, or whatever is very, very important.
That's, I mean, I could not agree more. I did not mention that explicitly, but for the channel estimation part, you have to use a fixed number of training symbols. I mean, you don't need to know them.
Yeah.
You don't need to know them, which is the good thing, but they have to be there. They have to be always the same symbols. And then with this, say, pattern and the received signal, then you can estimate the channel. And a related problem is that, well, if channel changes, then what? Do I have to retrain? Yes and no. What we are, say, looking at these days is about transfer learning approaches, which means that you train the system with some channel conditions, and then those channel conditions vary Then we attempt to use the set of weights that you obtain with the first channel conditions, and then try to adjust, to tune, to tweak it in order to make it usable for the other channel conditions with transfer learning approaches.
Then after comes the question, do we do learning for learning or maybe actually, because here you have the optimum and you have some time of learning outside parallel. No? Here you have an overlapping.
The optimum, I mean, you just say
it's not optimal. This is the conventional one.
it's maximum likelihood detector.
Yes.
The best thing you can get, I mean.
Yeah. And then you have the DNA here, which is the,
Those two curves, red and magenta.
and here there is no something green.
No, 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 no.
In the shadow. Okay.
It's no, it's
Sometimes we find that even of training, which is, I mean, for complexity, can pay, yes. Otherwise, the condition is fine.
well, what is not accounted for here is the training time. I agree with you, but well, assuming that you have, say, a good computer, I mean, to do the training, and assuming that you have some schemes like transfer learning ones that allow you to, say, transform the initial weights to some other weights, which can be used in a different environment, well, I think this is affordable. So, but it's true that the training part, the complexity of the training part is not accounted for here, just the performance. What are we considering? What? Sorry. No, this is something that we are thinking of. We tried something, but it's.
Or wireless study, especially because we are very far for this time. So if you want to train, you need to go for high frequency. The learning can be a restart point. So you have to start from scratch in what some other tools
And speed up the training for the other channel conditions.
can save time, can save if you convert this time in the amount of
Energy for training.
data, you don't have to amount.
Exactly. Well, I'm happy to discuss about those things. I mean, because it's something we are looking at these days.
Okay, so if there is no more question, thank you so much, Carlos, for this nice.
Again, my pleasure. Thanks for the invitation. Sorry, maybe it took a bit longer than expected, but well,
Thank you.
thanks for you guys. I tant. ¿Me desconecto, Carlos?